Hello, good afternoon. The topic of my presentation is MILP, a versatile method for production optimization. The agenda for the presentation is a brief introduction followed by several examples and then conclude with question answers. So what is optimization? Optimization is an efficient search technique to determine the best for a system. And the best is defined as an equation called an objective function, typically maximize profit or minimize cost. And system is defined by a set of equations called constraints or model. Production optimization is applying optimization to the operations of production systems. Production systems are chemical processing plants, refineries, plant utility systems. And here we are focusing not on the unit operations or subsystems, but on the entire system. So such large systems are characterized by surplus capacity, meaning there is spare equipment. So there may be 4 boilers and only 2 may be required during typical operation. There's flexibility in operation. Same equipment could be operated in different modes of operation, such as high and low severity for a reactor. And there are non-intuitive trade-offs. These may not be obvious to the operating staff, but the optimizer will search through and find the very best. So what are the different types of optimization problem? They are broadly classified along the lines of linear versus non-linear. So in the linear category, you have linear programming, LP, and MILP, mixed integer linear programming. A property of the linear optimizers is that they guarantee global optimum, meaning the optimum you have found cannot be improved. You can be confident of your results. So we talk about linear. What's a linear form? Linear form is something like AX plus BY plus CZ, where A, B, and C are constants, think numbers, and X, Y, Z are variables to be determined by the optimizer. So MILP, a general formulation is going to look something like this. There's a very compact notation. You have one objective function, only one, and this is a linear form. And you have many constraints. I'm saying M constraints, and each one is a linear form. Since these are equations, they're right-hand side. And these could be equalities or inequalities, greater than, less than type, or inequalities are okay. Most of the variable, the X, Y, Z's, are going to be floating point, but some would be restricted to binaries. That's where the mixed integer part comes in. So the problem in optimization is to convert your model into a set of equations. So that's an important question. Some of the great thinkers of our time have pondered over this question. And one such great mind was George Box, a famous British mathematician. And he said something very profound. Essentially, all models are wrong, but some are useful. See, reality is complicated. Model is an abstraction of that reality, and in no approximation is going to be perfect. So you can always nitpick any model and find deficiencies in certain areas. But that's not the right mindset. The right mindset would be to judge the model in terms of its usefulness. So when developing models, the focus has to be on the usefulness of the model. So how do we go about representing the complexity of your system in mixed integer linear equations? And I have a couple of guidelines. One is to keep the scope of your model as large as possible. And you might say that I'm complicating the problem. I'm making as large as possible. But the reason is the larger systems are more useful. They show non-intuitive relationships, non-intuitive trade-offs. So by expanding the boundary of your system all the way to the plant fence, you also deal with real economics. You have to deal with contractual prices with external suppliers. There are no assumed pricing for intermediate streams or transfer prices. And you have a large system. How do you manage the size? And here the guideline is to start simple and add complexity as needed and gradually. Next, we're going to see some examples. How do we go about develop good models? So the first example is going to be a boiler model, also known as a steam generator. And when you think about boilers, most people think of an efficiency curve. This is what the manufacturer supplies you. And it looks like an upside down parabola. It's a quadratic. So does that pose a problem? Unfortunately, it does. We want to keep the formulations linear or mixed linear so we can get a global optimum. If you have a nonlinear model, the global optimality goes away. So what can we do about this situation? So let's think about efficiency. Efficiency is basically energy usefully absorbed versus total energy supplied. In our context, the energy absorbed is going to be the heat of vaporization times the steam generated. And the energy supplied is going to be heat of combustion times the amount of fuel. So essentially, these two are constants. So efficiency is proportional to steam divided by fuel. So there are only two fundamental variables, steam and fuel. We can drop efficiency out of our consideration and focus on fuel and steam instead. So let's see what kind of relationship is that. If you plot fuel versus steam for a boiler, curve is going to look something like this. It's way more linear. There are no peaks. And it can be approximated by linear segments that is shown in the red there, very closely approximated. And you can have as many segments as you want. And an interesting property of these segments is the slope is increasing as you increase the steam load. You're going to use that fact later on in a slide. Okay. So what is our simple model based on what we discussed here? Let's assume a real relationship between fuel and steam. So that is this relationship. Then the limits provided for the steam generation, B1 and B2. So steam production has to be between those two limits. And the total steam produced has to meet the demand of the process. So is this a good enough a model or is there a problem? Unfortunately, there's a problem. What is that? The problem is that this boiler cannot be turned off. It's always going to produce between B1 and B2, and B1 is not zero. So what can we do about it? Let's introduce a binary variable. They're good for this purpose, on, off. So X equals 1 means boiler is producing, boiler is on. X equals 0 means boiler is not producing, it is off. And we can revise our model. Just multiply the constant terms by X, and this model is going to represent two operating regions. One would be just the operating point, the origin where steam is 0, fuel is 0, boiler is turned off, X is 0. And other would be the normal operating region, X is 1, and boiler is producing steam between B1 and B2. So we got two operating regions, but we are not limited to two operating regions. We could have more operating regions. So another interesting operating point is when the boiler is standby. It is not producing steam, but consuming steam and is ready to produce on a very short notice. So this would require another integer variable, call it y. Y equals 1, boiler in the standby mode. Y equals 0 is not in standby mode. And we can update our model. In this model, you can analyze it. It represents 3 operating regions, 1 and 2 as we discussed before, and operating point 3, which is the standby mode. It's consuming its fuel, but not producing any steam, but ready to produce on a short notice. Okay, so this was still, assumption was a linear fuel versus steam relationship. The relationship could be more nonlinear for your boiler, in which case you can approximate it by multiple linear segments. Here I'm showing 3 segments. Each one is a straight line. You have the equation for the line, and the model can be modified. Okay, the performance equation could be replaced by these 3 inequalities, and this would close. This will just follow this curve. Okay, completely. Again, we don't have time to discuss this, but you can test it for yourself. Okay. Okay. So this was the boiler model. There's also, you can solve it in Excel. This slide gives the details, but we don't have time to get into that. Let's move on to second model, which is the purchase fuel model. Again, I'm advocating we go all the way to the fence. So we're dealing with contracts. Contracts can be complicated. Here are some examples. The one we're going to discuss called volume discount. Okay. So if you purchase fuel any more than a given amount, then you get a price discount. So the supplier seems to have surplus fuel and he wants to incentivize you to buy more. See how we're going to model that. And again, we can define 2 regions. Region 1 where the rate 1, the higher rate applies, and region 2 where the rate 2 applies. Okay. And we're going to define 2 binary variables, x1 corresponding to the region 1, x2 corresponding to region 2. And we're going to put a constraint, x1 plus x2 is less than equal to 1. Okay, so we can be in only one region. And we're going to put some additional constraint that the fuel gas 1 has to be less than B1, and fuel gas 2 has to be only applies when you greater than B1, okay, criteria. So this set of model, these equations model this particular behavior of the contract. Again, there's a Excel model, and you can see the details in there and you can play with it. But we're going to move on, limited time. So next, so far, this is all single time period model. Time was not a consideration. There are situations where time becomes important, such as when you have inventory, and we're going to consider one case here where energy is being stored. And this happens in CSP, concentrating solar plants. The fact is that the sun is shining in the daytime, but the bigger demand in the nighttime. So you use the solar energy collected during the daytime when the demand is low and store it in a molten salt thermal storage system and use that energy when the demand is low in the evening or night and produce power when it's needed. So typically you consider 24 hourly period, 24 hours in a day. There's only one objective function, and this would be the summation of all the profit. Actually, in this case is, profit for the 24-hour period. And constraint, there'll be 24 constraints, one for each time period. And the constraint is to do with how much thermal storage is there in each period. So the starting value would be the period price period, and how much solar has been collected this period, how much has been produced by the fire heater, and how much is being consumed by the power generation. Then there'll be limitations on period. Each period there will be limitation on how much is the thermal storage capacity, what is the capacity of power generation, and some constraints could be over the entire region or entire period. So summation of the power produced of heat generated by the fire heater is limited to be 20. Okay, and so this is a subsystem, but the solution I'm going to show you for the CSP, and that looks somewhat like this. Okay, just focusing still on this thermal storage. In the red is the solar power. Okay, so this particular day, this is the expected solar power energy collection. And in the blue is the rate curve. Okay, so you have peak rates, morning rate, and even bigger peak rate in the evening. So the incentive would be to produce as much as possible in the evening. And you can see the thermal storage is charges up before the evening and discharges during the evening and maximizes the profit that way. Okay, let's consider another example of multi-time period. And here the constraint is that the boiler cannot start instantaneously. There's a delay. Let's say one time period, 1 hour delay. So how do we start modeling? Start with the boiler without delay. The previous boiler we had, and we could repeat it for the n periods, okay? So the models are getting bigger, n times what we had before. And to model the delay, think about delay. Delay means the boiler can be turned on, status 1 in period t, if and only if it was either standby or already up in the previous time period. And the boiler cannot be cannot be turned on if the boiler was off in the previous prior time period. And this logical constraint captures it, okay? xt is less than equal to xt minus 1 plus yt minus 1. And this also applies to more than one time period delay. Here is the solution for a contrived problem, demand in period 3 and 4, 8, 9, and 10. And the boiler does the right thing. It goes in standby period before when the demand is, steam is needed. Okay, so much for examples. In terms of conclusions, I hope you got the feeling MILP is a versatile modeling method, especially for large systems. It gives a guaranteed global optimum. Functions do not have to be continuous. We saw multiple operating regions. Variable initialization is not required. This is an issue in nonlinear programming. And for nonlinear function one dimension, such as the efficiency curve or fuel versus steam, you can break it down into multiple segments. And similar technique can be applied for multivariate nonlinear function. It's not discussed here. We saw logical constraints can be applied. Again, very powerful. Technology is mature, robust, inexpensive commercial software is available. A limited version is available in Excel. Execution is fast for well-defined problems. And as the example showed, it applies very well to optimization of utility systems, but it also applies to other production systems and the combination of production system and utility system that we did not discuss here. Well, so much for the presentation. Next, we're going to get into Q&A.